this. So as you see, today I'm going to talk about baryon fractions, but also about feedback. And the key thing is I believe these two topics are very tightly related to each other. And so I will spend 1 minute to remind us why and how of this, and then I will go straight to the point. So let me start from this very famous plot very briefly. So this is the baryon fraction within galaxies as a function of halo mass. And we all know that within galaxies, the amount of baryons is much less than the total amount of baryons nominally associated to their halos, which means that most of these baryons must be kept outside of galaxies somehow, most likely by some sorts of feedback. And now the two important related questions are how, so what kind of feedback exactly, and where. So for instance, what fraction of these baryons are outside of galaxies but just in their vicinity in the circumgalactic medium. So this is just a pictorial representation of what I mean. There are, broadly speaking, two kinds of options. First option here on the left is that you have some sort of strongly ejective feedback, which removes the baryons not only from the galaxies, but also from the halos altogether. And in this case, you expect to have a low baryon fraction not only within the galaxy, but also in the circumgalactic medium. The second option is that you have some gentler form of feedback, some maintenance mode, which keeps the baryons outside of the galaxies, but in their close vicinity, within the virial radius of the halo. And in this other case, you expect to measure a higher baryon fraction within the circumgalactic medium. So the idea is if you measure the circumgalactic medium baryon fraction, you can put constraints of feedback processes. And this is the main motivation of this work. Now, this idea is not at all new. For instance, it has been extensively studied in the context of constraining AGN feedback at redshift 0. This is one example by this study by McCarthy. This is, again, baryon fraction as a function of halo mass. This time, this is masses baryon fraction of hot gas within the virial radius of groups and clusters. The black points are observations. The color points are predictions from different models with different AGN feedback. And the idea is that you tune the parameters of the AGN feedback to reproduce the observations. And another very famous example is the example of Illustris. The first version of Illustris was failing miserably to reproduce these observations because it had too strongly ejective AGN feedback and too few baryons within these halos. And this was indeed one of the motivations for changing the recipe in the improved version of the TNG Illustris simulation, which apparently works better with respect to this. And, but all of this was just to explain that the general idea is not new, it's a very well-known approach to feedback. But now I would like to ask, can we try to do something similar to constrain other feedback processes? So for instance, star formation feedback. And most importantly, can we try to do this kind of test not only at redshift 0, but at higher redshift? At higher redshift is very important because most relevant physical processes happen there. So first of all, what should we expect at high redshift? Zeroth order expectation is that we have very strongly ejective feedback from supernovae, which eject baryons from halos at very high redshift. Then these baryons with very high efficiency, at least in many implementations. And then these baryons take a long time to be reaccreted back. So Avishai yesterday mentioned robust predictions. This, as far as I understand, is a relatively robust prediction of this scenario, is that as long as you look at sufficiently high redshift, say redshift 3, where the baryons didn't reaccrete yet, you should have relatively speaking, a low baryon fraction in the CGM, 30–40% of the cosmological value. And this is just an example, but many simulations and studies find similar results, as long as you have very efficient ejective supernova feedback. Now this is probably more or less correct. Is it possible that there are refinements to this theory? Personally, I don't know. But in the recent years, as you know, there are people have been increasingly investigating other physical ingredients in addition to this. So for instance, cosmic rays, or maybe there is the option that the cooling function is not exactly the one that people usually assume in some conditions. Then there are some sorts of radiation pressure. The list could continue. These are just examples. But what these kind of physical ingredients have in common is that in general they prevent some excessive star formation within galaxies without requiring enormous ejections of baryons from the halos. So if one or more of these things are really important, it is conceivable that one could expect larger baryon fractions in the circumgalactic medium. So it's interesting, I think, to try to at least attempt to make this measurement because it can put constraints on this kind of scenarios. So of course, at this point, the key question is, all right, but how do you measure the CGM baryon fraction at redshift 3? So this is very, very difficult, of course. But in this moment, it's not complete. It's starting to be not completely impossible. And the reason, of course, all of you listened to Sebastiano's talk, which was the last talk yesterday, and the first talk about the CGM session, in a sense. And so you know that the way to do this is to use fluorescent Lyman alpha emission in those regions where we can see it, meaning close by to very luminous quasars. Now I don't need to explain again how this works, but I just highlight very briefly what are the main results. The main results is that we see these giant Lyman alpha nebulae everywhere we expect to see them, so close by to luminous quasars. These nebulae are huge, they really extend on circumgalactic medium scales, and most importantly, they are very, very bright, much brighter than what was expected based on simulations, at least until a few years ago. And what is the reason of this? Well, of course, the simplest explanation is that there is a lot of gas in these halos, at least a lot of cold gas, which is the one that can emit Lyman alpha radiation. But now we would like to know, okay, is this true? Is it not? How much cold gas do we have precisely? And most importantly, how much gas do we have in total? Because the gas that is visible in Lyman alpha and the total gas are not necessarily the same thing, and I'm coming back to this in 1 minute. So I said that these nebulae are very bright. So the key question, of course, is what determines the surface brightness of fluorescent Lyman alpha emission? Fluorescence means recombination radiation. This is very well-known physics. This surface brightness depends essentially on these parameters that I underline here. One is the filling factor of the cold emitting gas, the temperature of the emitting gas, because the recombination coefficient depends on that, and of course the density of the emitting gas. All of these parameters are important, but of course because of this square dependence that you see here, the most important of the three is the density of the gas. So this brings me to this question, which is probably the most important question of this talk. What determines the density of the cold gas in the circumgalactic medium? And broadly speaking, the most important processes are two. First, gravity, of course. The second is very important, is pressure confinement. And let me summarize this with this plot taken from a recent paper. So these are phase diagrams, so temperature, density. We saw some of these plots yesterday. Take, for instance, this blob. This is, suppose that this is a patch of gas at the virial temperature and the virial density, so what you would expect from gravity alone. If you have cold gas embedded within this is going to be not only much colder, but also much denser, because it's going to be compressed by the pressure of the ambient medium. And the two are related by this line, this green line, which is an isobaric line of constant pressure. And the key thing is that this cold gas will be confined to a very small fraction of the volume and organized in clouds with very small size. So if you want to see this with simulations, you need very high resolution. And indeed, yesterday we had this excellent talk by Nir, who showed us that simulations are now starting to reproduce this behavior. And the thing that I find interesting is that this is one of a few examples where the numerical simulations are struggling and only in the end succeeding in reproducing the analytic theory rather than vice versa, which also happens sometimes. But the analytic theory is correct, is very fine, and you can use it to interpret the observations if you want. So what do you do if you are an observer? You take the surface brightness of Lyman alpha emission, you use it to infer the density of the cold gas, which is the one that emits Lyman alpha, and then you can climb back this green line to infer what the properties are of the rest of the medium that you don't see, because it's too hot to emit Lyman alpha. And this is essentially the basic idea of the model that we use to interpret the giant Lyman alpha nebulae. So this is the summary of the assumptions. This model of the giant Lyman alpha nebulae is based on these two assumptions. First, that what we see is recombination radiation. Second, that the CGM is a multi-phase medium which obeys this simple physics that I summarized in the last slide. This model has three parameters. One is the filling factor of the cold gas, which is related to the density because of the compression, as I said. Second is the temperature of the emitting gas, because it is related to the recombination coefficient and therefore the emissivity. And third parameter is the halo mass, which sets the overall scale of the problem. So now in the last minutes, I will show what the results, meaning what the total mass of the CGM that we infer from the observations, depend on these three parameters, one at a time. So the dependence on the filling factor can be summarized in this plot. This is a log-log plot. On the x-axis, you have the filling factor of the cold gas that you assume. On the y-axis, you have the mass of the circumgalactic medium that you infer from the observations under the assumptions of our model. The red line is the cold gas only. The blue line is the hot gas only. And the black line is the sum of the two. So as you see, there is a broad range of possible results. So on one side, you have very low filling factors of the cold gas, which means very high density of the cold gas, and a large amount of hot gas that you need to keep it confined. And on the other side, you have a completely volume filling cold phase without any hot gas, and therefore the cold gas in this case dominates also the mass budget. Now, what is interesting about this plot is that you see this horizontal line is the maximum possible that you can have, which is the cosmological fraction. So not the entire range is physically plausible. Only a limited fraction of the filling factors makes sense. And the other interesting thing is that this curve has a minimum. So even if you don't know what the true filling factor is, you can use this model, if you believe the assumptions, to put a lower limit to the CGM baryon fraction that you need to explain the observations. However, of course, this plot is just an example because it's done making some assumptions on the other two parameters, which are the halo mass and the temperature of the cold gas. These are also important, so my almost last slide is to tell you how all this picture changes when you change these parameters. So this is the temperature of the cold gas. If you increase the temperature that you assume for the cold gas, the baryon fraction that you infer increases. This is because the recombination coefficient changes. And if you want to obtain baryon fractions that are significantly smaller than cosmological, you can do it, but you need temperatures that are significantly below 2 × 10⁴ Kelvin. And this sounds very reasonable in general, except for one thing that we have to remember, that these nebulae are observed are illuminated by construction by very luminous quasars. And if you take these into account and you do the photoionization modeling, you find that the thermal equilibrium temperature in these conditions is rather higher than this. It's 5 × 10⁴ Kelvin or so. So it's not easy to reach this low amount of masses. And the similar story happens for the halo mass. If you change the halo mass, the baryon fraction change. And if you want a very low baryon fraction, you need halo masses that are pretty large, 5 × 10⁻² solar masses, which is also sounds plausible, except that at least, the most recent results, and the most accurate, these are estimates of masses, of halo masses based on quasar clustering, and this is by far the most statistically significant study because it contains 20,000 spectroscopically confirmed quasars at redshift 3. I don't know if this study is correct, but it predicts halo masses that are on the low side. So if this is true, it's again not easy to accommodate the observations with low baryon fractions. So now I'm just going to summarize these results. To summarize the results, I will just take for each of these models just the minimum, so the lower limit on the CGM baryon fraction that you infer as a function of these parameters. So this is the thing. So halo mass here, temperature here of the cold gas here, and the color code is the baryon fraction. So this, if you want to agree with predictions of storm-energetic feedback, you can easily do it, but you need high halo masses and low temperatures. And but as I said, both thermal equilibrium in photoionization field of quasars and quasar clustering seems to bring this constraint towards this black line, which is the cosmological baryon fraction, possibly suggesting that you have some sort of gentler feedback processes as a possible interpretation. And this is just a summary. You, in general, use CGM baryon fraction to constrain feedback models. If you are a simulator, please provide this prediction. Giant Lyman alpha nebulae are a great observable that can make us learn many things about the CGM, including this particular question. And at least this analysis that we did suggests that there is a lot of baryons in these halos. And thank you for your attention.
Thank you. Can the next speaker come up? Yeah, first question in the front.
Hi, Gabriele. Quick question. When you assume the density and the temperature of the cold gas, and you say you go back along the isobar and you infer the properties of the hot gas, do you assume that the temperature is at the virial temperature of the halo?
Very good question. So the zeroth order answer is yes. But the first order answer is not really. If you change you expect the temperature to be close to the virial temperature. But if you change it a little bit, you expect to see a difference in the density profile because of the hydrostatic equilibrium equation. And then because the cold gas is in pressure equilibrium with the hot gas, also the density profile of that changes. And that has a consequence on the surface brightness profile of line alpha that you can constrain from the observation. So this effect is included in our models. All our plots include this effect. It's not huge anyways. Yes.
Is it quick? Okay, go ahead.
Maybe a naive question, but isn't there, again, these dense cold clouds, isn't there self-shielding to the line alpha, and therefore you're more sensitive to the surface area of the dense gas rather than the total volume density?
No, the reason is that the quasars are so luminous and the distance from the quasar is so small because we are looking at CGM scales that in order for that effect to be important, we calculated you need densities of the order of 10 to the 4 centimeters to the minus 3, which are absurd.
Thank you. Okay, our next talk before the poster presentations will be from Jonathan Stern on cooling flow solutions and the onset